In this class, we will talk about using urine or urinary data for determination of some of kinetic parameters, and the same model that we are still talking about, which is one compartmental model. One compartmental model, single dose of IV bolus with a linear kinetic of the elimination. Okay, so we are still talking about the same model, but rather than using the blood, as we already mentioned earlier, and the equation of the that we used from sampling from the blood, at which we had concentration in the plasma or versus time at different profiles, right? We had rectilinear, we had this, which is the profile that we are having on rectilinear using the blood sample. Okay, so this is what we already did or studied before in our previous classes. Okay, for now, we will use urine data or urinary excretion data to determine some kinetic parameters. One of them is the elimination rate constant. Okay, we already know that urine is one of the samples that is commonly used and collected to determine in kinetic study in general, and it's a non-invasive technique. Usually, sometimes it's convenient um, uh, for taking them as samples, but sometimes it's not comfortable for the individual to give urine samples. And we talked about this earlier. We will have a little bit more comments or notes about urine sampling from a kinetic point of view. But let's just now have it as kinetic and the equation related to the kinetic of the drug. So I will use the same model that I have. And again, I have here the amount of the drug remained in the body, but we will talk only about the excretion rate constant. Okay, so the amount in the body that is excreted. Okay, and if we remember, here we had elimination rate constant, and under first order kinetic, this was excretion and metabolism, right? This is what we mentioned earlier. So we will talk about only what is happening through excretion to the urine. Okay, so if I will write the differential equation of the rate of excretion. Okay, excretion. So just remember that we are now talking about excretion rather than total elimination. Okay, as the amount excreted in the urine over dt. Okay, so this is xu, amount excreted in the urine, okay, at certain time. So in terms of, we want to use this as in terms of the amount in the body, and this constant, which is excretion rate constant. If we want to remind ourselves with something that we did in the introduction of the rates and orders of reaction, it's similar to whatever we mentioned, but I'm just talking about something that is increasing, okay, rather than something that is increasing. So let's go back here and just have it as in terms of amount and rate of excretion. First of all, we have amount in the body that is increasing at this side, okay? And it's the rate constant would be excretion rate constant, okay? And again, if we remind ourselves that the this is the excretion rate constant, that is first order for sure, okay? And this is the amount of the drug remained or available in the body at time t. Okay, so now I have this equation in terms of that the rate of excretion, it's positive because the amount is increasing in the urine with time, and I have it in terms of the excretion rate constant and the amount in the body. Okay, so I will just rewrite it again here. So let's rewrite our equation. Again, we have, don't forget that we are talking about excretion, and this is rate of excretion. Okay, so this is our differential equation. We know from our previous studies or our previous classes that we can have this in different terms, right? Or we can determine what is the amount in the body. Just as a reminder, let's consider it as self-reminder that the amount in the body, right? And again, we are still talking about this model of IV bolus, one compartment, and single dose with linear kinetic. So we were able to determine the amount in the body using this equation. So what if I just substitute this here? Okay, let's do it. So dxu equals ke multiplied to the amount initial, to amount initial in the body multiplied to e to the power of minus k multiplied to the time, right? So if we look at this equation, we have an equation with a mono-exponential term, and it's with minus here, so it would be mono-exponential profile, and it's decreasing. Can we take the log or len for both sides? Yes, we can. So let's take the log to the, it's similar to whatever we know earlier, but the difference is your y is different, but still your x is t. Okay, so before taking the log or len, let's just draw this profile. Okay, so okay, I will have rate of excretion versus time. Again, I'm drawing this as my y, and this is my x on rectilinear profile. According to the equation that we have, what would be your profile? This would be again monoexponential, and decreasing. The difference is your y-intercept is multiplied to x naught. Okay, can we have it under semilog or on semilog profile? Not, sorry, semilog profile. I won't transform it yet. So semilog dxu over dt versus time, it would be, because we are following first order kinetic, and the y-intercept again is x naught multiplied to k excretion. Just be careful in this and those kind of profiles that we are talking about excretion here, and we are talking about rate constant of excretion in the intercept. Okay, so what if I want to transform the main equation that we have to log or len? Okay, let's just rewrite the main equation that we have, which is dxu over dt, which will be okay. Again, just don't forget, this is the excretion, this is the total elimination rate constant, and this is the excretion rate. So please don't forget this and keep this in mind. Okay, if we want to transform the rate of excretion to log term, okay, this would be log right? Just think about it, right? Then multiply to the time, right? F, which is, again, this is, we will draw it in 1 second. This is y and this is x. If I want to have it in len term, this would be len minus k multiplied to the time. This is your y, this is your x. So let's draw both of them, or sketch. Let's sketch both of them. We are on rectilinear profile. We will have log excretion rate, or len excretion rate. Okay, this is log t, 1 sec. Okay. Oh, I didn't write it here, but this is dxu. Okay, let me check if I wrote it here right. Yes. So it's the rate of change in the amount excreted in the urine per unit of time. This is just, I missed it here, so correct it. It's the rate of change in the amount excreted in the urine per unit of time, in both of them. Okay. So again, this is the same here, ln dxu over dt versus time, okay? Versus time here and versus time here, okay? So if again the profile was giving me a mono-exponential profile on a rectilinear graph, then if we transform it to ln or log, if we are having a first order kinetic as we assumed earlier, then we will have linear profile in both of them. The difference in the y-intercept, if we are talking about log, our y-intercept would be log xe multiplied to x naught, both of them, log this term, okay? If we are talking about ln transformation, our intercept would be, y-intercept would be the ln of this term, okay? If we want to have, the slope, for sure the slope we will have it from the linear regression, but the slope here would be equal to minus k over 2.303, and the slope here would be equal to minus k, okay? So if you notice from those profiles, we were able to determine k, okay, which is first order elimination rate constant, and again, just be careful, it's total elimination. When we are talking about k, it's total elimination. And we also are able to determine ke, which is the excretion rate constant. So be careful, it's the excretion rate constant. In some references, you will have it as xu, what is excreted in the urine, but we will use so on from now ke as the excretion rate constant. But let's keep it as a note here. Some references use ke, or other references use ku, okay? Which is again, in our case, is the first order, and it's excretion rate constant. So notice, again, just be careful and keep in mind this is excretion, okay? Just notice that we were using the rate of excretion in from the urine. So we were using urine data, okay, to determine those information or those parameters. So we were able to determine both of those rate constants, which are parameters for the profile for the model that we are having or studying, okay? And just again, be careful that k is determined from the slope and ke is determined from the intercept, but you need to take the anti-log, if it's a log transform, to that term, and then just take it out to determine the ke. And in ln transformed, you need to take the anti-ln of the term that you have, then take out calculation-wise, just back calculate the excretion rate constant. Okay, we know from whatever that we know earlier that if we know k and we know ke, we will be able to determine the metabolism rate constant, right? Which is sometimes, let's be a little bit more specific. If we consider, 1 second, let me just tell you a note before we go into the metabolism rate constant. When we said elimination as a process, it's both excretion and metabolism. right? Excretion is majorly in renal system, right? In kidneys. And metabolism is majorly happening in hepatic system and the liver, right? So if we are talking about rate constants, we are having K as elimination rate constant. Here we are talking about Ke, but we are talking about excretion in the urine only. The metabolism, we usually have it in not only in the hepatic. If it's hepatic, it would be equal hepatic, right? Metabolism is usually everything is happening not only in the liver. If it's only in the liver, we call it hepatic rate constant. Sometimes this is called non-renal, okay? Non-renal rate constant, which is anything that is outside the excretion system, okay? But you got the point. It depends of whatever is happening per drug. But anyway, let's consider, according to whatever we mentioned here, that we have um, elimination rate constant, total elimination rate constant, and we have excretion rate constant through whatever is excreted in the urine. So if we have this and we have this, can we determine this according to whatever we know earlier? If we remember, we know that K is equal the sum of all K's of different processes that we have, despite the process of its metabolism or excretion, right? So if we have the elimination rate constant, we can just subtract the excretion rate constant. So we will able to determine the metabolic or non-renal rate constant. And this is usually the way to determine or to assess or approximately determine the non-renal elimination rate constant or the metabolism rate constant. Okay. Now I will just talk about an important note about the excretion rate constant, or when we use the urinary excretion rate to determine K and Ke, or the determination of those mean parameters. Okay, so again, we said that we use the urine, whatever is excreted in the urine, as rate of excretion as amount excreted in the urine per unit of time, right? And when we had it, it was so according to the profile, let me just sketch the profile rate of excretion versus time. This versus this, okay? It is giving me this profile, which is the mono-exponential profile. According to whatever we mentioned so far, we are at each time point, right? We are considering that that amount of urine is excreted at that exact point, right? But this is not true if we are talking about the nature of the urine collection, because usually the drug in the urine is collected over a period of time, which means that if we are at 0 time and we had it at 1 hour, the urine that we are collecting according to the anatomy of the urinary system or renal system, the urine is collected in the urinary bladder. It's a collection of the urine through this time interval, not at 1 hour, exactly at that discrete time. No, it's a collection of the urine that is collected in the urinary bladder for that time. So there is so many ways to correct for that to make the estimation more accurate. And one of them, we will talk about it, which is what is mentioned in your textbook, which is in your book by pharmaceutics and by Shargin. Okay. There are so many ways to correct for that again, but we will consider this one as the one that we will use, in which we will take average rate urinary drug excretion against the average time. Okay, and there is so many ways to use it as symbols, but what we usually have, we will correct for it as numbers, then we will show you how we will do that. Let me go to the slides to make it easier for you to go with me. Okay, so let's see here. We have a time. Oops. We have time. We have concentration measured at certain time. We have the amount excreted in the urine. We have the amount excreted over time interval. Okay, it's time interval, and we have T star. Sometimes it's just T prime, and sometimes you will have it as T slash. Okay, in hours. So what is that we are having here as let me just see here. Okay, what we did. This is okay. As time interval, one thing that for correction of the time, we are using the each time interval minus the time interval before it, which means 0.25 minus 0, 0.5 minus 0.25, 1 minus 0.5, 2 minus 1, 4 minus 2. So we are correcting for the time to have it as time interval, okay? This, we usually call it the average rate constant, excretion rate constant. Then we use the mid time point or the average time point, in which we are having both time points, the exact time point and the one before it over 2. We call it sometimes the mid time point or the average time point. So we correct in this way, we are correcting the time as itself on the x-axis, and we are correcting the rate excretion or excretion rate on the y-axis to make it more accurate to do it. So if we just then use or draw the average, now we call it the average rate, excretion rate, okay, versus mid time point, which again it's may call T prime or T star, okay, so we call it mid time point or average time. Sometimes you will have this again according to your reference as du over dt over t, sorry, or xu over t, or sometimes you'll have it as average, okay, something like that. So it depends on the reference that you're having, but we just keep it, as I mentioned, according to the reference as average excretion rate. So you may have it as this versus t prime or like this, or T star. The profile as per se, if you are doing it, it will be the same. So it will be on rectilinear as mono-exponential decreasing profile. And the same thing if you have it on semilog, on length transformed or log transformed, as we just draw them. But it will be the estimation of, let's say here, the y-intercept, we will use it to estimate, um, right? It will be more accurate estimation because whatever that we are having is in intervals. So we are dealing with intervals of sample collection, urine sample collection, rather than just the exact time point. So we were correcting for that in this way, but the exact profiles or exact y-intercepts and slopes will be the same, but the estimation of those parameters are more accurate now because we correct for that point. We will talk a little bit about now we will talk a little bit about the difficulties in urine data collection, or as, let's say, some comments on using urinary excretion data and kinetic. First of all, we know that, as we mentioned, first of all, it's non-invasive way of sampling, but sometimes we need to take into consideration some points when we are dealing with urine as a sampling or as a sample, or its procedure of analysis. First, first of all, when we are talking about urine sampling, we need to have a significant, if we are talking about, again, we are talking about excretion, right? So when we are talking about excretion, we are talking about unchanged drug that is excreted in the urine. So to use this method, we need a significant fraction of the drug that is excreted unchanged in the urine to be able to detect it and measure it. And for sure, this should be a significant fraction to be able to analyze it. Again, to do so, we need an assay technique that is specific for that a fraction of the drug that is excreted unchanged um, from in the urine. Another thing that, if we are talking about the profile that we need to draw as rate of excretion versus time, we need to have frequent sampling to have that profile accurate, right? And blood sampling, even it's an invasive way of taking the sample from our individual, but it's more easier compared to sample collection. So we need as frequent samples as we can, which is sometimes not feasible, let's say practically. Okay, um, we need this samples to be collected until almost the entire drug is excreted, and we will keep this point of, for a couple of seconds until I show you the table of the excretion percentage or elimination percentage. But usually in practice, we need like 95 to 99% of the drug to be excreted and the urine, which is similar to the elimination of the drug. Again, we need 95 to 99 because usually it's the for this is more than, we need around more than 95% or more than 99% of the drug to be eliminated. And this is happening at 5 half-lives and 7 half-lives. Usually in practice, it depends on the researcher of or the and the clinical study that we are doing. Usually, as a rule of thumb, we use five half-lives as enough time because we are getting more than 95% of the drug excreted at that time. So we need a significant fraction of the drug to be excreted unchanged in the urine. We need a significant and specific analysis method. We need as frequent sampling as we can to make the profile as accurate, kinetic wise, and we need the duration of time that is enough for the almost the entire drug to be excreted. There is some of the challenges that is related to the urine itself and the nature of the urinary system that is affected um, uh, by the intake of the fluid or a drug or food. So the pH of the urine is a little bit variable according to the intake. Usually daily intake of drug, food, or drinks. In addition to the volume is affected by whatever it's variable according to the if the fluid intake is large, so the volume of the urine would be large. Another thing that we need to take into consideration is the subject variability, as the urine collection, uh, according to that, should be instructed accurately to the individual to make sure that the way of the sample collection is the same and complete sample collection is happening. So those are points that we need to take into consideration. I will stop at this point and we will continue in our next class.